Hi, these are some solutions for problems from the beginning of Chapter 12 about equilibrium. Static equilibrium, that is. Balanced forces, balanced torques. First couple problems, you do not need to use torque, like number 3. So we have this situation here. We've got a sphere. It's being supported by a cord that's attached to its center, like this. And this distance here is L, which is 8 centimeters. And the radius of the sphere here is 0.042 meters. That's the radius. It's held in place by a massless rope. The mass of the sphere is 0.85 kilograms. And they want us to find the tension in the rope and the force on the sphere from the wall. Alright, so what are the forces? Let's do a force diagram here. The forces acting on the sphere, we've got, and there aren't any torques here. You can see all the only forces acting on the sphere are acting here, basically at the center or along the radius, so there's no torque there. That wouldn't make it rotate. And then this also perpendicular force from the wall, so there's no forces that are causing any torques. We have this tension force, gravitational force, and then the normal force from the wall. 0.042 meters is the radius. This is also a radius of the sphere. So that means that if I wanted to find, let's say, this angle here, theta, so that I could break up the tension force into its components, then I can find that angle theta because I know this is 0.042. Right, and this is 0.08. So theta, we've got the opposite and adjacent sides. Theta would be equal to the tangent inverse of 0.08 over 0.042. And that, my friends, is 0.08 over 0.042. is about 62.3 degrees. So that means if I wanted to write my balanced force equations, the forces in the horizontal direction are balanced. What are those forces? Well, there's the cosine component of tension, T cosine of 62.3. and that would have to be equal to the normal force. And then also the forces in the vertical direction are also balanced because the thing ain't moving. So that means that gravity, mg, must be equal to the sine component of the tension force. And sorry, that's not theta anymore, it's 62.3. So in this equation here, I know everything. I know the mass of the sphere is 0.85 times 9.8 is equal to T times sine of 62.3. So I can divide that over here and find the tension force, which I think is what they want in A. That the tension force is 0.85 times 9.8 divided by the sine of 62.3. So that's 9.4 newtons. And in B, they want to know what is the normal force. And I've got an equation here. So the normal force is the tension in the cord, the horizontal component of that, which is T cosine 62.3. So it's this times the cosine of 62.3. And that's about 4.4 newtons. And that's all there is to that. Number 5. A rope of negligible mass is stretched horizontally between two supports that are 3.44 meters apart. An object of weight 3,160 newtons is hung at the center of the rope. The rope is observed to sag by 35 centimeters. What's the tension in the rope? So I've got this situation here. I've got the tension in the rope. Remember, tension acts at both ends of the rope, and it's equal both sides. Doesn't double. That got some of us in trouble recently. And then I have the mg, and the weight. They actually gave me mg, right? They're giving me the weight of the object, so that is the gravitational force. And this distance that it sags here is, let me draw a triangle here. So I've got, here's half the rope. And I know that this distance is 0.35 meters. And the rope is 3.44 meters. So half of 3.44 meters is 1.72 meters. There's half the rope there. So let's see, I have the opposite and the hypotenuse. So theta, the angle here, would be equal to the sine inverse of 0.35 over 1.72. So exciting. You get to use all of this wonderful trigonometry that you learned. And you might have wondered, when would I ever use this? And now you get to use it. Well, that is 11.7 degrees. So that means here, these would be the cosine components, and these would be the sine components of the tension force. So the sine components, there's two of them. So those two sine components, 2t sine of 11.7 degrees, would have to balance the gravitational force. That's our tug of war there. Two upward components of tension, excuse me, balancing gravity. So if I want to know tension, the tension is 3160 divided by 2 times the sine of 11.7. So the tension is about 2 sig figs, and be 7,800 newtons. And book has 7,900 newtons, so I guess that's somewhere for some difference in rounding. So I'll let you figure out what that is, but this is fine. All right, let's flip around here. Number 7. Now we're going to be using some torque considerations. A 75 kilogram window cleaner uses a 10 kilogram ladder that's 5 meters long. He places one end on the ground 2.5 meters from a wall. So here's the building, the wall, so he places the ladder here. This is 2.5 meters. This is 5 meters. You might recognize that that would make it a 30, 60, 90 triangle. This would be 60 degrees here. And the mass of the ladder is 10 kilograms. And the mass of the guy, how about the mass of the man? There you go. Is 75 kilograms. he's 3 meters up the ladder, so he's somewhere like 3 meters, about here up the ladder. When the window breaks, neglect friction between the ladder and the window, so no force there, no force this way of friction, just the pressure from the window, and assume the base does not slip. When the window is on the verge of breaking, what are the magnitude of the force on the window from the ladder, the magnitude of the force on the ladder from the ground, and the angle relative to horizontal of that force on the ladder. Okay, now I'm going to do similar to what we did in class. I'm going to make a force diagram of the ladder, but I can't make the ladder a point because it matters where these things are acting, where the forces are acting for the purposes of torque, right? So here's the ladder. At the center of mass of the ladder, we have the gravitational force, mg. Half a meter past that, because that'd be 2.5 meters up, right? Halfway up the ladder. Here, there's another force, which is the mass of the man times g. That's the gravitational force of the man on the ladder. There's the force from the window, and then here at the bottom, there's the two components, call it Fx and Fy, just like we did in class. So there's a bunch of forces here. And I am going to write all three equations, like we did in class. So what do we have? We have the sum of all the forces in the x direction is 0, right? Just at the instant before the ladder breaks. So that would give me Fx is equal to Fw. Those are the horizontals. Sum of all the forces in the y direction is 0. That would give me an equation that Fy would have to be equal to mass of the ladder times gravity, put a little L in there, and plus the mass of the man times force of gravity. So I could find that right now, so why don't we go ahead and do that. So see, that would be 9.8 times the two of those. The two of those combined would be 85. So, but that's 833 newtons. That would be that force, right? And then here I can't do that yet. I can't do anything with that because I don't know what that is yet. I know that those are equal, but don't know what they are. So let's write the net torque equation. Net torque, not rotating, so net torque would be 0. Now I got to pick the axis, and since I don't know anything about these right now, but I do know these two, I'm going to do the same thing that we did before. I'm going to pick the axis here. To write my net torque equation, because that'll knock these two forces out of the equation. So let's see. I have 3 torques here. These two are trying to make the ladder rotate this way, and this one is trying to make it rotate this way. So that's the fight. So on one side of my equation, I have the force, mass of ladder times gravity, times the radius at which that force is acting, which is 2.5 meters, times the angle between force and radius, which is 30 degrees. It's actually 150 degrees, but you can always use that to supplement, and that works. Sorry, I need sine in there, sine of 30. So that's that one, and then there's another torque from the guy, which is the mass of him times gravity times the radius at which that acts, which is 3 meters, times the sine, again the sine of 30 degrees, and that's going to be equal to the torque from the window force, which is window force times the radius, that's at the full length of the ladder, sorry, kind of creeping into the other side here, times the sine of the angle between these, which is 60 degrees. So that's an equation there. I think if you wrote that equation right, that's worthy of a pat on the back. So I can solve for the window force. That's the only unknown in this equation. So the window force would be all this stuff divided by 5 sine 60. So let's do that. So the mass of the ladder times 2.5, times g times 2.5 times the sine of 30, which is 1/2, plus the mass of the man times 9.8 times 3 times the sine of 30. All that divided by 5 sine 60. That's about 283 newtons, looks like. Oops, 283 newtons. The force on the window. And I lost track of what A, B, and C were. Let's go back and look at that. Part A, magnitude of the force in the window. So that's part A, right here. That came from our net torque equation. And then part B, they would like, what's the magnitude of the force on the ladder from the ground? The magnitude of that force. Well, notice here that Fx is equal to 283, right, because those were equal. And that Fy, we found up here, is 833 newtons. Right, so the magnitude, these are the two components of the force on the ladder from the ground. Right, there's this, which would be a frictional force, and this part, which would be more like a normal force, right? So the magnitude of the total force is the Pythagorized sum, or vector sum of those, right? So that would be the square root of 283 squared plus 833 squared, which is about 880 newtons. And in part C, they want to know what's the angle. So anytime we want the angle of a force and we have the components, it's tangent inverse rise over run, vertical or horizontal. And that tangent inverse 833 over 283 is about 71 degrees. So 71 degrees above horizontal. Cool. That's a good problem. That's similar to what we did in class with our suspended beam. All right, next, number 9. We have a meter stick that's balanced horizontally on a knife edge at the 50 centimeter mark. So it's uniformly distributed, we would assume, with 2 5-gram coins stacked over the 12 centimeter mark. The stick is found to balance at the 45.5 centimeter mark. They want to know what's the mass of the stick. So I'll do a force diagram for the stick. The where are we putting the coins? Over the 12 centimeter mark. So let's say this is the 0 centimeter mark. So at 12 centimeters, we have 2 coins. Basically, there's a mass there, and there would be gravitational force from that. Magnitude mass of the coins times g. Now the meter stick itself has mass. We pin that right at the center, and they told us that it balances at the center, so that is where the center of mass is. That's the mass of the stick times g. And then we know that it's balancing at the 45.5 centimeter mark. So it's balancing there. That means there's a normal force, an upward force on it here at the 45.5 centimeter mark. and we could call that a normal force. So those are the forces. Excuse me. And we don't know the mass of the stick, right? That's what we would like to know. So I guess the question here, and I don't know the mass or the magnitude of this either, but I don't necessarily need to know that. They're not asking me for that. So I think that the art of solving this particular problem is picking the axis. So let's think about this. I don't know this, but I don't really care about it either. So that, I think, would lead us to think that that would be a good choice for the axis. So let's think about that. If I chose that for the axis, then the two torques, that'd be this torque, if I make this the axis right here. This torque would want to make the stick rotate this way, right, because it's on that side of the axis. This torque would want to make it rotate this way. So those two torques, since it's balanced, have to be equal. So I have this torque. I have to be careful. Remember when we report our distances, our r's, for our torques, it's the distance from axis to where that force is acting. So on this side, we have a force of mass of the meter stick times g times the r, the radius at which it's acting. This is at the 50 centimeter mark, and this is at the 45.5. So that would be times 0.045 meters. Force times radius, and it is acting perpendicular, so the sine, I'll write it out here, but it's going to be 1, right? Sine of 90 degrees. That torque would have to be equal to this torque, which is torquing the other way. So that's mass of the coins, which we know, times g, times the radius. The distance between this and this is 45.5 minus 12. That would be 33.5 centimeters. So 0.335 meters. That's force times radius times the sine of the angle between them, which is again 90 degrees. So let me rewrite that equation, plugging in what we know. Mass of the stick times g, notice that the g's cancel on both sides, so I'll just get rid of those, times 0.045. That's got to be equal to mass of the coins, 2 5-gram coins. So that's a total mass of 10 grams, or 0.010 kilograms. The g canceled out, times 0.335 times the sine of 90 is just 1. So there you go. There's the equation we can solve for the mass of the stick. We chose a good axis. 0.01 times 0.335 divided by 0.045. So it looks like it's about 74 grams. That is the mass of the stick. Number 11. Figure 1227 shows a diver, weight 580 newtons, standing at the end of a diving board with a length L, 4.5 meters, and negligible mass. That seems kind of questionable that the diving board would have negligible mass, but we'll go along with that. The board's fixed to 2 pedestals that are separated by a distance of 1.5 meters. Of the forces acting on the board, what are the magnitude and direction of the force from the left pedestal and magnitude and direction up or down of the force from the right pedestal? And which pedestal is being stretched and which is being compressed? Okay, so make a diagram of the diving board here. I've got one pedestal attached here, and there's a force there. I don't know whether it's up or down, so I'm going to wait on that. And then there's another one here That's 1.5 meters away. Again, it's attached. It could be up or down because it's attached, right? Could be holding it down, could be holding it up. Don't know. And then the diver here, there'll be a gravitational force from the diver of 580 newtons. They gave us that. And the whole length, this would be like another 3 meters. The length of the whole board is 4.5 meters. Right. Okay, so this is the one on the left. So let's consider here for a second. I know that the net torque is 0, and if I pick the axis to be the right pedestal, then if this was the axis, then the torques must be balanced, right? There's this torque and this torque here. So those would have to be balanced, which means that since this one is making it want to rotate this way, the other one would have to be wanting to make it rotate this way. So this force has to be down. It has to be. So if that's the axis, then the equation would look like the torque from this, I'll call this force of the left pedestal. It would be force of left pedestal times the distance from the axis, which would be 1.5, times the sine of theta, it's 90 degrees. I'm just going to leave that out now. We've seen that enough times. And then this one, this torque, would be the 580 Newton force times the radius at which it's acting, times the sine of theta, again it's 90 degrees. So the force on the left pedestal, I might be doing these out of order, we'll see, but is 580 times 3 divided by 1.5, which is 2, so 1160 newtons, and that's down. The force in the right pedestal, now you can actually just use the forces in the up-down direction have to be balanced. So I think we know what the force on the right pedestal has to be now without doing any torque business, because the vertical forces, you have FL and the 580 Newton force down would have to be balanced by the force on the right pedestal, which would have to be up to balance those two. Right? No torque considerations there. That's just basic balancing of forces. So that means the force on the right pedestal is going to be equal to 1160 plus 580, which is 1,740 newtons, and that is up. And they said something about which one's getting stretched and which one's getting compressed. So this one, the force on this one here on the board from the pedestal is down. That means the pedestal would have to be pulling down. So if you imagine the pedestal is sort of attached to it, if the pedestal's pulling down on it, that means the board's pulling up on it by Newton's third law. So that means the left pedestal is getting stretched, right? Because it's having to pull down on the board. So this is a stretch. And by the same logic here, if this pedestal's pushing up on this one, that means the board's pushing down on it, so it's getting compressed. And if you kind of imagine the situation, I don't know, I hope that there's some intuition that this is all correct. It seems very much so to me that if you got the two pedestals there and the divers on the end, that this one's going to be getting pushed down and this one's getting pulled up because the whole board wants to go, right? Would want to rotate like this if there was nothing attached there. And I think that's the answer to all the parts. Let's see what the parts were again. So magnitude and direction up or down of the force from the left pedestal. So that's A, B, magnitude and direction up or down of the force on the right pedestal. That's C, D. And then which pedestal, left or right, is being stretched. So that's E. And then compressed is the force on the right. Or the pedestal on the right is getting compressed. Compressed, that's not a word. Compressed, that's a word. Let me just check the answers here, make sure I didn't steer you wrong there. So that's good. Down, that's good. Up, and then left and right. Yep. All good. Cool.